already talked about it.
So I'm going to say that it's going to be there's no experimental data here, right? This is an exercise. So I don't think you need to do the full metal jacket write-up methods, results, all that kind of stuff. If you did that, that's fine. But I would say that this should be just enough information that you could reproduce what you wrote a year from now. In other words, it's notes to yourself. The second lab is going to have real data and real analysis, and for that we want a full write-up. Also, there's various ways in which the circuit in lab 2 will be modified. Right? You probably won't use the time constants I specified because they're marginal for what we're doing here, the time constants of the filters. So I talked about last, wow, it's a long time ago, last Thursday, I think. Did I talk about that Thursday or Tuesday? Tuesday. So you're going to want to talk about how you modified the circuit. There are various things you can add to the circuit. I think that the basic circuit I gave was a sensor and then a combination of amps and filters. So what comes out of here now is an analog signal which is proportional to the opacity of your finger. Wouldn't it be nice to, and of course the main point of this lab is to do the next steps in software to threshold it or to fast Fourier transform it, but you could also imagine extending the circuit to do some of these functions automatically. So for instance, let's say we put a comparator in here. A comparator, and then an LED to ground. Then you could make a nice little blinky light. It blinks once for every heartbeat. But for a comparator you need two inputs, right? You need a threshold and you need a signal to compare against. Now this signal is going to vary quite considerably depending on the geometry of your finger and how you happen to be breathing. So what is the appropriate threshold for this? Some mean of the signal, right? It's some line that goes through like that. Oh, well that looks like a low-pass filtered version of the signal, right? So the other input of the comparator might be something that looks like a low-pass filter with a fairly long time constant, 5 seconds. So what's going to come out of here then is going to be pulse, rest, pulse, rest, pulse, rest. That's where you wiggled your finger. How could you convert that? Let's say that you wanted to make a completely analog, no computer, completely analog pulse rate meter. What would you have to do to that pulse train to turn it into a heart rate? Because this is kind of like, it's probably almost a constant duty cycle, but not quite, right? It depends. Your heartbeat is a little bit chaotic. Some beats are a little bit longer than others. There's some noise in here. How would you turn that into a rate? Timer? You mean a 555 timer? Okay, how would you do that? Yes, I mean, yes, you're right. Now, what would you do with a 555 timer? You know, everybody know what a 555 timer is? The most used integrated circuit in the world.
Count the number of periods between two lines.
But that's not analog exactly, right? How are you going to count? Well, all right. What does count mean? Count means integrate, right? An integrator is a counter for voltage. It adds up the number of, if you had all pulses the same size and then you integrated the area under them, the number that you integrated would be proportional to the rate.
Why couldn't you feed this to a capacitor to charge it?
And you, so you could, if the duty cycle were constant independent of frequency. I'm not sure that's true for hearts. I think that if your heart rate is low, you're going to get a waveform that looks like this. If your heart rate is high, you're going to get a waveform that looks like this.
Change the capacitor charging.
But would that work? Maybe that would work.
That would change the capacitor charge.
Yeah, it would change the capacitor. Maybe it would work just directly. Be an interesting thing to try. Yeah, all right, so one possibility is to take this output and make it into a pulse train with fixed pulse length independent of duty cycle. So now you take the rising edge here and you make a pulse which is always the same length, one pulse per heart stroke. Then when you integrate that, you will certainly get a rate.
How about something like a triac? You trigger something like a triac motor.
Yes.
And the triac is switching a voltage that's constant.
So a triac, once it's switched on, never switches off until it goes to zero. So you charge a capacitor through a triac or something. Yeah, it could work. Yeah. A triac, a silicon-controlled rectifier. It is a voltage-controlled switch. The symbol looks like this. It's a voltage-controlled switch. Once you put a pulse of a certain size on the control line, this becomes a short circuit as long as voltage is applied. When you remove voltage, it turns itself off. So it's a very nonlinear resistor. Anyway, making the world's simplest pulse rate meter might be an interesting final project if you could make it accurate. Let's say you hook up a digital voltmeter to this thing. Everybody's got digital voltmeters. Buy one at Harbor Freight for $3. Right? Hook up a digital voltmeter to it, and it reads in heart rate. That'd be fun. It's a fairly simple project, but there's other things you could do too. You could put another 555 timer on here and run a beeper, so it goes beep, beep, beep. So all of your partners are foaming at the mouth. Okay. Any questions about the pulse rate meter? We're starting at this week. It's a 2-week lab. Some of you have already started it. Did it work? Did you get it running? Got it running. Okay. I'd say a goal for this first lab period is to have the circuit completely running by the end of the lab, so you can do the signal processing before the next lab.
Is there the ability to put together a circuit and then store it somewhere for the next week?
Oh yes, thank you for reminding me. If you grab a whiteboard out of the cabinet, and cabinet 2 from the left has a stack of whiteboards in them. Grab one of those whiteboards, put your name on it by pinning a piece of paper with a wire on it, and if you stand at the door of the lab and look way back in the left-hand corner, there's a putty-colored cabinet, a tan cabinet, that is for student projects. Just put your named board up there and nobody will touch it.
So can we just put it in a box like in 47?
I'd prefer you to leave it in the lab. unless you're going to actually like work on it outside the lab. But problem is, I lose about 30% of the boards a year in 4760 because people take them out. Pardon me?
You want to keep their project for their parents.
Yeah, well, it's so much work, I don't want to take it apart. I can understand that. It took me, when I took data for my PhD, it was on film because there were no computers then. So I'd open the shutter on the camera, fire the oscilloscope, close the shutter, open the shutter on the camera, fire the oscilloscope, close the shutter, one frame at a time. And then you had to analyze these under a microscope, 25,000 frames in my case. And it was years before I could throw away that film. It was totally useless. I'd analyzed it. I just couldn't tolerate throwing it away because it was so much work. I finally did. I got over it. Any other questions about Lab 2 at this point? So we're going to talk more about op amps now. We're going to be using op amps for the rest of the semester in various ways. And we want to talk about some of the clever circuits people have built using op amps, some of the limitations of op amps in the context of biology. And last time we talked a little bit about differential amplifiers and the reason why we need differential amplifiers. The main reason being that in biological systems there's often a lot of common mode noise. So you got your dish sitting here with your fish in it, and you're recording from the fish and from ground into some sort of differential amplifier. And then there's a ground lead that goes out here, and there's some small resistance, but there's also a 60 hertz AC noise pickup from just the environment. This 60 hertz is now referred to as a common mode voltage in the sense that it is applied to both the positive and the negative input of the differential amplifier. And if the differential amplifier is a perfect subtractor, this noise completely disappears. And so, which is referred to as having good common mode rejection. Any questions about that? We talked about that in some detail, I think, on Thursday. But any questions about that? I drew out the circuit for a standard 3 op amp differential amplifier, but I didn't go through the analysis. Maybe we ought to do that, just for fun. So the standard 3 op amp differential amplifier, this is, by the way, what's in an INA 121, which you will be using in Lab 3, is a very interesting topology where these two op amps act as impedance buffers. So no current flows into either of the positive leads, so you don't have to worry about what resistance you're hooking up here. There's no current drawn, essentially no current drawn from the preparation. And so if we have V1 here and V2 here representing the positive input and the negative input, we would like to know what kind of voltage comes out of here. To analyze this, we're going to call this R1, this R21, and this R22. The subscripts are to imply that under most conditions R21 and R22 are going to be about the same size. And easiest way to analyze this is to set this to V out 1, name this node V out 2, and then compute the difference of these two. So we know that V1 here must be the same as this voltage, V minus 1. And V2 must be the same voltage as V2 minus, because the op amps are going to supply the current necessary to make that true. In that case then, V1 is equal to V minus 1. But what's the value of V minus 1? Well, let's just assume we have some current through these three resistors in this direction. Then V minus 1 is going to be V out 1 minus whatever the voltage drop is across R21, which is going to be R21 times I. But I has to be V out 1 minus V out 2 over the sum of the three resistances, R21 plus R2 R1 plus R22. Right? So V1 is equal to V out 1 minus R21 times V out 1 minus V out 2 over R21 plus R1 plus R22. And now we're going to calculate V2, which by a similar argument then is going to be V out 2, and then what? Plus R22 times the same current. Conservation of current says the current through this resistor has to be the same as the current through this resistor because no current flows into either one of these inputs. So, and if current is flowing in this direction, this voltage must be higher than this one. So we add. Now, what we're going to do is say, well, let's just subtract these two. So we're going to calculate then V1 minus V2. Which is given by V out 1 minus V out 2 times 1 minus R21 plus R22 over R21 plus R1 plus R22. And we can fiddle with this algebraically, but we can already see that the detailed balance, that R21 does not have to be exactly equal to R22, because these two resistors only appear as a sum and never as a ratio. And we can mess with this and turn it into V out 1 minus V out 2 is equal to V1 minus V2 times 1 plus R21 plus R22 over R1. Since R1 is usually pulled outside the package, this allows us to adjust the gain over a rather large area. If we just don't connect R1, then it has value infinity and the gain is 1. as we lower R1, we get a higher and higher gain. So then we can directly write the common mode rejection ratio. Common mode rejection ratio, well, we need the output for a voltage which is the same on both inputs, and then an output which is different on the two inputs. We know that the gain here, if the two voltages are different, is 1 plus R21 plus R22 over R1. Question is then, what is the gain if both these voltages is the same? Well, if the voltages here are the same, then symmetry says there's no current flow through these resistors. And so this voltage must be the same as this voltage. And so the gain is unity. What? So the gain is unity. So for common mode, for equal input, the gain is unity, and this becomes the common mode ratio, rejection ratio for the first stage. So if you were to operate this system at a gain of 100, then the common mode rejection ratio would be 1/100th. And for the INA 121, these four resistors are matched within 0.1%, which gives you another factor of 1,000 common mode rejection. So the actual common mode rejection of the whole system then is the input stage times the output stage, which is about 0.001. Any questions about this? This is a pretty good differential amplifier.
So that's only valid if V1 equals V2?
This is the value of V1 equals V2. So that's the common mode gain. This is the differential mode gain if the two voltages are different, which we just showed over here. The common mode rejection ratio is the common mode gain divided by the differential mode gain. The differential mode, the common mode gain for this stage depends of the second stage depends on the matching of these four resistors, but because they're completely inside the package on the same substrate, they can be laser matched and laser burned to the right resistance and are quite stable. So this is the kind of head stage you will find inside of almost every physiological instrument that's hooked to humans. EEGs, EMGs, ECGs, or all have some sort of differential amplifier. But let's consider a different situation. Let's just questions. Any questions on this? You can be using this over and over again. There are versions of these, by the way, which are isolated, so that you hook a voltage here and a voltage here, and you get a voltage out here, but there's no electrical connection between the input and the output. And this can be done in at least three ways. It can be capacitor coupled, it can be inductively coupled, or it can be optically coupled. And I'm going to have you build an optically coupled system for Lab 3. Rather than use an off-the-shelf one, I'm going to have you build an optically coupled system where the output of the amplifier is not ohmically connected to the input of the amplifier. Now, another situation that comes up fairly often in physiology is that you're trying to record from something small. Now, we're not going to do this so much in this class, but in electrophysiology classes, let's say you took BioNB 4910. Some people have done that. Who's done that? You've taken 4910. 4910 is BioNB 4910 is a fantastic electrophysiology class. It's really good. It shows you how to record from all kinds of animal cells, and I think plant cells too. Electrically active plants. But one of the problems they have in that, now here's the canonical dish, but in this case now I'm going to draw a mussel in here rather than a fish. You're sticking a microelectrode into this mussel and then trying to record the potential that comes out of it. This would typically not be differential, be single-ended, but there would of course be a ground in here with some noise source. And some gain on the system. If you're intracellular, if you're actually getting an electrode intracellular, the voltage changes are going to be on the order of 100 millivolts. So the gain doesn't have to be awfully high here. It might be a factor of 10 to get it up into the kind of volt range. But one of the problems with this is, let's now expand this out down here. We have a cell or some small structure. We're sticking a microelectrode into it. That's probably not the scale. If you stuck a microelectrode that big into a cell or some other structure, it would kill it immediately. Like, you know, it's like, as they say, it's like trying to record from a cat with a telephone pole. But you have these electrodes, to the degree to which the electrode is smaller than the structure that you're recording from, its resistance must be higher. So there's some series resistance. As you drop this aperture down to a wavelength of light or so, the conductance path gets small, and so the resistance must get large. And there's some small series resistance out of the cell with some sort of voltage source here to ground, and this is kind of the Thevenin equivalent voltage source you're trying to measure. So you have a very high resistance here. That's okay. That's good. That makes it a good voltmeter. Right? High resistance is good for measuring voltages. And we go up to this electrometer amplifier, which draws almost no current into its input. But there's a problem, and that is that it's very hard to get this distance smaller than a few tenths of a centimeter. And typically it's on the order of a centimeter. And whenever you have a wire in space, you have a capacitance to ground. That means you've just built a low-pass filter here for the voltage coming from the cell.
Is it not possible to shield these wires? Because
It is possible to shield the wires, but we need to do this carefully. So, is this a problem or not? Well, the resistance here could be on the order of 10 meg to 100 mega ohms, and the capacitance could be on the order of 10 picofarads to 100 picofarads or so. So the time constants could be as high as 10 to the 8th times 10 to the minus 10, or about 10 to the minus 2 seconds. Now, the action potentials in many cells are on the order of a fraction of a millisecond long. So the rise times are on the order of 100 microseconds or so, or about 1,000 times faster than that. So with this kind of low-pass filtering, you won't see the action potentials. They'll just be little tiny bumps. So what do? Well, as Amrit said, one thing you can do is shield this. So let's say now that I won't do erasure, I'll just draw another one. Let's say we were to now take this wire and the electrode and put a shield around it to ground. It's now worse because the ground, which are this small capacitance, was originally caused by coupling to metal structures that were a foot away, and now you've moved them to a millimeter away. And now the capacitance is increased rather than decreased. Damn. All right, that doesn't work. But, we know this is V plus, right? This is V minus. We happen to have here a source of voltage which is at the same voltage as the center conductor. So why don't, instead of putting this to ground, why don't we hook this shield to the negative input of the op-amp? Now we're guaranteed that the voltage on this shield, and we can run this all the way down along the electrode until just before we get to the water, and people do this. Now, if we hold the voltage on the shield exactly equal to the voltage on the center conductor, whatever capacitance is there can't charge, right? You're locking the charge accumulation at 0 because the voltage difference is 0, and so you've nullified the capacitance. And this is called a driven shield. A driven shield, where you find in the circuit a point that is fairly low impedance and has a voltage equal to the voltage you're interested in shielding, and you connect it. Okay, there is a resistance in series with this point, with V minus, and so it does take some amount of time to charge this capacitance through the output voltage. But if you use any kind of reasonable feedback resistor, let's say 100 k ohms, then the time constant is a factor of 1,000 lower or so, and so the charging of this is essentially instantaneous. However, there is a small transport time through the op-amp. There's a charge transport time, so that there may be a very short transient. If you put an input that changes like this, you may see some fairly short transient before it comes up to final value. But you can even do better than a driven shield. So if you're worried about capacitance, if you're worried about bandwidth, the first thing you always do is add a driven shield to the system. The next thing you do is to add a negative capacitor. This is sometimes called a capacity neutralizer or a negative capacitance compensator. Sometimes it's automatic, sometimes it has to be set by hand. But the basic circuit looks like this. Now we're going to abstract away the biology and just say that we have some electrode resistance, some V cell, and ground, we have some electrode capacitance to ground. And for concreteness, I'm going to set the gain of this amplifier to 10, 9R and R. And we're going to add a little bit of positive feedback. So we're going to call this CF and VF, where VF is some fraction. This is a potentiometer. It's guaranteed to give a fraction of the output voltage. So we're going to say that VF is alpha times V out, where 0 is less than or equal to alpha is less than or equal to 1. Because a potentiometer is always a fractional gain. All right, so let's now, we're going to say this is a low resistance, you know, on the other hundreds of kilo ohms. So the driving point impedance on this is low compared to everything over here. So this is a constant voltage source effectively. This is a constant voltage source. So we can then redo this as, we can rewrite this circuit as V cell RE CE going to ground, V in and because I set the gain to 10, this is then alpha times 10 V in, which is equal to V out. So if we have some current flowing in from the cell, not much, but a little bit, then the current, no current flows into the input node of the op-amp. It must then flow out. Oops, there's a capacitor here, right? Capacitor CF. It must flow out through this capacitor. Conservation of charge says that the current either flows out through one of these two capacitors, I1 and I2. And we know from conservation of charge that I1 plus I2 is equal to I. And we know that I has to be equal to Vn over so I1 is the current flowing through this capacitor. The impedance of the capacitor is 1 over j omega CE. Everybody knows that terminology. Plus I2. I2 is flowing out here, so it must be V in minus 10 alpha V in over 1 over j omega CF. So what if, by changing alpha, when we change alpha, let's make alpha an adjustable knob on the front panel here the human gets to set. Let's say we change alpha, can we find a position of alpha such that the current through the two capacitors adds to 0? If we did that, if there was no current through the capacitors, there's no time constant. You're not charging them. Time constant goes away. The system becomes infinitely fast. Now there's some consequences of infinite fastness, infinite quickness, but let's deal with the mathematical condition first and then talk about the practicalities. So 0 equals I equals V in J omega C E plus V in minus 10 alpha V in times J omega CF. Well, we can simplify this quite considerably. As long as omega is not 0, we can divide through by omega. As long as Vn is not 0, we can divide through by Vn. And so we find that CE is equal to plus 1 times 1 minus 10 alpha times CF. So 0 is equal to CE plus 1 times 10 alpha plus CF. Or, if we set now, so if we rearrange this, we can see that if alpha is equal to 1/10 of CE over CF plus 1, current will be 0. The time constant will go to 0. The system will have infinite bandwidth independent of the input capacitance. Well, that's kind of cool, but what happens in practice when you do this? Anybody want to hazard a guess? What happens if you turn it up a little too much? Say again?
Oscillates.
It oscillates. That's right. So as you approach optimality here, the system is going to become unstable. So if you were to start out with a waveform that looks like this, because you're putting a square wave into the system, and you start turning up alpha, you're going to get something that looks like this. You're going to lower the net time constant. You turn it up a little bit more. You turn it up a little bit more. Let's see, where shall I put this? Turn it up a little bit more. You're going to get something that looks like this. And you turn it up just a little bit more, and you're going to get something that looks like this. And you turn up a little bit more, and you get something that looks like this. It's going to go to square wave oscillations. So if you were a physiologist looking at this system, you'd want to adjust it someplace between here and here, just so the system rises rapidly but does not overshoot. Now, that's the good news, is you can mathematically zero the time constant, but nothing is ever free. Right? This is like you've just gotten rid of the entropy of the system or something. So what is the cost? Anybody want to guess? Apart from the noise is the cost. Yes. And why is that noisy? Why is this circuit noisy? You want to try and think that through, or shall I tell you? You want to try and think it through? So you've turned up the high frequency gain, effectively. You've turned up the high frequency gain because you now have almost infinite bandwidth. That means any noise of any frequency at all will be amplified, including stuff that's way outside the bandwidth of what you're interested in.
There's no filter.
No. There's no filtering at all. There's no low passing at all. Secondly, but it's worse than that. It's worse than just amplifying the thermal noise from this resistor. And all resistors have thermal noise. You amplify the internal noise of the op-amp itself now quite considerably at high frequency. And the transport delay through the op-amp itself becomes highly significant and destabilizes the system. So you can't actually get to perfect squareness, because if you do, something else will blow up. The system will start to oscillate too soon. So there's limitations here. There's noise limitations, but it allows you to choose the trade-off between noise and bandwidth that is best for your particular application.
Why not use the shooting trick instead?
You use both. So you shield first. You use a driven shield first. You can get rid of almost all of the capacitance that way, except down near the tip of the microelectrode, which is underwater, which you can't drive. But for that, you can negative capacitance feedback. You can negative capacitance cancel. There's also usually a little bit of capacitance around the terminals of the op-amp itself that are hard to shield away.
Maybe I'm forgetting my basic op-amp stuff, but why can't you just put a high-pass filter if you're trying to measure, if you're trying to amplify something and put a high frequency that's coming in? Or you still have to worry about the high frequency?
So if you were to, right, and so in a sense, this is an adjustable high-pass filter that you're hooking on here. And so what you're saying is, what is the advantages of this circuit over taking this waveform and putting it through a high-pass filter? I think the advantage is, I mean, this is an interesting question. I believe that the answer is that if you take the output of this and then put it through a second op-amp, you have 2 op-amps worth of noise. Whereas this way you have 1 op-amp's worth of noise. But that would be interesting to work through in detail. I don't know the answer on that one.
Since the noise tends to be of higher frequency in the op-amps, would that come into play there?
It does, yes. Yeah. So this way I say you're only getting 1 op-amp's worth of noise.
There is an option of selecting between a high bandwidth and amplification.
High bandwidth and high amplification. So if I were to turn this up to 100 times, what does it mean for, so we have a gain of 100 here. What does it mean for the circuit? It means that we have to drop the value of CF if we're going to have adjustability, because otherwise this ratio will be very close to 0.
Is there a sweet spot for the circuit where there's a moderate amplification and moderate bandwidth?
Is there a sweet spot? There is a sweet spot for adjustment here, which is not a function of gain, but is a function of the feedback strength, which will give you a moderately good bandwidth and a moderately good noise. The noise increases very rapidly as you get towards 0 time constant. So if you can adjust it to the point where you get 90% of your signal and only 10% of the noise of going the next few percent, then that's where you want to be. Now, can you adjust it automatically? Because this does get tedious to adjust. By the way, in the old days, back in the old days, that would have been 1940s, they didn't know this trick yet, so they just swapped out capacitors until they found one that worked. That's really tedious.
Is there some way to measure noise digitally? Because then you could do it.
You can certainly measure noise digitally. You can certainly calculate the power spectrum of the noise coming out of there and adjust the system for whatever you decide is an optimum power spectrum. One small problem with this system is that if you accidentally turn up the voltage, turn up the feedback to the point where the system is oscillating at full amplitude, this becomes a current injector into the cell and blows up the cell membrane. In fact, some commercial amplifiers have a thing called a buzzer on it. You push the button, you put the electrode against the cell but not in the cell. You push the button, it jacks the negative capacitance feedback to full, blows a hole in the membrane, the electrode slides in. But that suggests that if you accidentally turn up the gain too far while you're inside of a cell, it just demolishes the cell, and it does. So your system, if you were going to do this automatically, you'd have to know a lot about the noise, and I'll bet you could classify it because the system becomes very high in high frequency noise as you jack up the gain at high frequencies. Becomes high noise dominant. So it could be that if you were to measure the spectrum of the noise coming out of this system, you could watch the tail come up, and just before it starts to flatten out at high frequencies, you stop it. I haven't tried that. Last time I used one of these myself, we were using PDP-11 computers, which were running at steaming 100,000 operations a second. So I didn't have enough bandwidth to even do an FFT on those machines. Nor did I think of doing that. But there's other interesting things to do with op amps too. And I think I'm going to draw a circuit that I misdrew earlier in the semester, so-called virtual ground. So you have your dish over here. You want a ground lead going in, then you have your electrode going off to some amplifier. And instead of putting the electrode directly to ground in the sense of hooking it to a piece of metal, oh yeah, we need to talk about shielding too, but typically these dishes would be on a steel plate, or you would have some sort of shield around the person, or you'd be laying on a steel bed or whatever. But the ground electrode is going to come off to the amplifier. The positive lead is grounded, and there's a resistor in the feedback. So any current through here becomes a current through here. So we get a V out, which is equal to minus I times R. So we can immediately determine the amount of current flowing into the ground line. That becomes important. Let's see. One of the preps I've seen people do is you open up a fish. You hook electrodes around a chunk of a nerve in their brain, and then down here, some distance away, you put on another pair of hook electrodes, or one hook electrode, and you fire a pulse through here, and then you measure what comes out of the nerve. And it would be nice to know the current you're using to stimulate, and you can get that by using a virtual ground. So you can sometimes measure stimulus currents by using a virtual ground. You can also look for ground faults. You can look for anomalous current flows due to noise sources. Because this is an active system, and this point is being driven to a ground by the op-amp, the impedance of this point can actually be lower than just connecting the ground to a steel plate. This can be a better ground, a better quality ground, than merely connecting this wire to a steel plate. One of the more interesting circuits you can build with an op-amp is this thing. So this point here, if this is V out, then the positive terminal must be at V out over 2, because this is an R to R voltage divider. And that means that V in has to equal V out over 2. The current flowing into the terminal, I in, would be given by V in minus V out over R1. So I in is then V in minus 2V in over R1. All right? Using this relationship, substituting V in for V out here, which means that we have that I in is equal to V in over minus R1. It looks like a negative resistor. In fact, whatever impedance you put here, this becomes a negative impedance converter. Just like a sodium channel. So this is a model for a sodium channel in the membrane. Do negative resistors bother you? Does this upset your EE soul in some way? Like conserving energy? But you don't have to conserve energy here, because whatever energy is necessary to make this happen comes in through the op-amp power supplies. And you only get a negative resistance so long as the op-amp can follow the voltage appropriately to force V out to V in. Once you get outside the range of the op-amp power supplies, then this goes back to being a regular old boring positive resistor. So if you were to produce the IV curve for this resistor, let's say we have V positive and V negative here. So the IV curve, V negative, V positive, it's going to look like this. It's going to be N-shaped, where this is minus R1 slope. So what happens if you build a voltage divider where this happened to be minus R1 and this is R2 and this is some Vn? Well, by the voltage divider equation, V out must be minus R1 times R2 minus R1 times V in. And so depending on the relative size of R2 and R1, you can get gain out of it. Let's say if R1 equals 1,000 ohms and R2 equals 900 ohms, then V out is going to be minus 1,000 over minus 100 equals 10 V in. So you can do all kinds of odd and strange things if you have a negative resistance. A long time ago, I used to teach an electronics course in neurobiology, in which I did something that I think they do in 2100 now. I gave the students little boxes with an unknown circuit in it, and they had to analyze what was in the box. And so I would give them a resistor capacitor combination, and they had to analyze it as a two node circuit, just like you would a cell, which has an inside and an outside of the membrane. And then I'd give them something with with two resistors and a diode in it, so it had a rectification, partial rectification. And then after they got good at that, I'd give them one of these with a couple of batteries in the box, two 9-volt batteries, and this, and they would go berserk trying to figure out what it was. Did they ever do that to you in 2100? Did they ever give you a negative resistance?
They didn't do that.
What'd they do?
They made it more of a competition, sort of. So when Mo and I taught up 2 years ago, we were learning ROC circuits. And so he gave us a bunch of black boxes with different combinations of ROC circuits inside them. And we had to just analyze the output and figure out what the circuits were inside.
Were those 2 terminal? Those were 4 terminal, right?
Yeah.
So you had something that looked like this, and did you know which 2 were input and which 2 were output, or which 2 were ground? You didn't know anything.
I don't think so.
It was just there were just 4 terminals in a square.
Possible combinations we could see. We could figure the numbers and stuff. So it wasn't completely black box. We had some idea of possible schematics.
I like that. That's a good lab.
I enjoyed that lab.
That's a real lab. I mean, it's not like wire point A to point B. Look at the oscilloscope. Wire point C to point D. Look at the oscilloscope again. That gets boring. But when you have to... Yes. It's reverse engineering the circuit, yeah. So we're training a whole generation of IP... What?
At some point you put a diode there somewhere
to make it. And at the point where you put a diode in, then it becomes nonlinear and extremely difficult.
Yeah. That was the hard box.
That's the hard box, right? So I would say that final projects for this class could be all analog. You could build a circuit. It could be all digital. You could write a program. It could be a combination of the two. It could be a device you carry around. It could be a simulation. If you wanted to simulate a magnetic resonance image machine, oh my God, that would be interesting to do. Pardon me? A lot of Fourier transforms. A lot of digital filtering to get rid of artifacts around the edges of the system.
I have a question. So, like, what's the deal with stuff that we make here and, like, Cornell policy?
You mean intellectual property?
Yeah, is it going to belong to them?
Interesting that you should mention that, because it came up. Well, it came up last night in the EC Innovation Awards presentation last night. Anything you do in a class that everybody has access to in principle, not everybody's taking the course, but in a standard routine lab that you do, where you do a project for a course using nothing but material found in the teaching lab, if you're an undergraduate, you own the property. If you're a PhD student, Cornell owns your soul, forget it.
Oh, really?
Yeah, it doesn't matter what you do. If you think of something really cool while you're sleeping, Cornell owns it.
I gotta talk to Roger.
Because you're an employee.
Because you're an employee of the university. Now, anything is negotiable, right? But that's the default if you're an employee of the university, which you are.
What about other grad students who aren't PhDs?
Masters of Engineering?
They still own it, right? I'm an MS, not an MN.
If you're a master, probably own it.
If Cornell is paying your tuition, then Cornell owns it. If you are paying your tuition, you own it.
Bruce, do you know that the MN just signed the intellectual property release form at the beginning of the year?
Everything is negotiable.
Regardless of that?
I think that you have a good case if you're self-supporting. You have a good case that you're not an employee of the university, even if you're a TA. That doesn't count. I think you have a good case that you own your intellectual property. And I know lots of MN students who have walked away with their intellectual property and Cornell does not have a hold on them. They're paying their tuition. They're not. I mean, yeah. So, for instance, specifically, I had a guy last year who was doing a project for SpaceX. SpaceX owns it, not Cornell. Allison Smith did a MEng project that's owned by her parents' company, not by Cornell. So you can defeat that. I think if you intend to, you should negotiate it up front.
So Bruce, in case of 4760, Cornell gave us $100 for each of the groups to build up a project, right?
They actually gave you $20.
Yeah, 20 and 80.
80 of your own money, yeah.
So in that case, you can still be owned.
Yes, you own your intellectual property for $47.60. That's a class project. It very clearly falls under the category of your intellectual property. Now, let's say that you wanted to get a patent on that, and then you could variously pay, depending on how you do it, something between several thousand and a couple of and $20,000 for the patent, for the lawyers and for the filing and so on.
What if we wanted to like do an improvement of a device from a company that would want us to do that?
As a PhD student,
You probably should get a
don't do
separate
it.
company.
No.
You mean negotiate up front if you're going to do that.
So what in case of in a group where one is PhD and another is master's?
Cornell owns it.
Yeah.
Sorry,
Absolutely, no doubt. If one member of the team is a paid employee, Cornell owns it. Now, Cornell will license it back to you for the appropriate term. The term is negotiable, but the nice thing is, the good thing is that if Cornell owns it, Cornell, if there's an IP opportunity, Cornell will pursue the patent and pay for it. And that can be worth $20,000 or $30,000 of actual money, depending on how you do it. Might be worth less, but it could be that much.
But anything outside the lab could be mine.
Anything,
Outside the lab.
anything you do at Cornell while you are a PhD student belongs to Cornell.
Okay.
If you think of
Well, at
it,
Cornell.
if you implement it in the shower, if you implement it, you know, you come up with some high-tech thing for your, Cornell owns it.
Really?
Yes.
But how did Rajat know? Because Rajat, when Rajat took, his research, and he gave a talk about this, when he took his research, and he got, the company and whatnot, what he did, even though he was using PhD students, I remember explicitly, he paid out of pocket for all like the lab time and like the tool usage and whatnot.
If you pay out of pocket, it's yours. So for the intellectual property, for the innovation stuff that we talked about last night is, let's say that you as a group get $10,000 prize to develop your project. You can then say, I'm going to write a check to Al Molnar for $1,000 to use his lab as for rent.
Exactly.
Then it stays your property. You are renting Cornell's property.
Exactly. That's what Rajat.
That's fine.
Okay. So I needed to know.
So I would like to
Basically,
give
it's an
somebody
idea
a
of write it
surprise.
down, put it in your closet, and then when you graduate.
Yes, money talks. Talk walks. Yeah, I'll be polite here.
Speaking of microprocessors, are we allowed to use microcontrollers?
I would say I will discourage microcontrollers in this lab. This is not a microcontroller lab. This is an analog lab. Analog, and computer analysis. I'm not going to completely rule out microcontrollers. What would you want to do?
Not sure yet. It's a good idea, but I want to know what options I have.
I guess I will say, if you can come up with a compelling reason to use a microcontroller as opposed to a desk machine, then I will allow that. However, I'm also going to say I'm not supporting microcontrollers in this class.
But we cannot do anything without a microcontroller. Most of the devices require a microcontroller.
What? For what?
For any processing or any display.
No.
Portability, I guess.
Portability, maybe. Although it could use a phone.
Do you support iPhones and Droids?
No, I mean, you're going to have to do that yourself. I support MATLAB running on the desk machines. This course is supposed to be analog input, MATLAB backend. You can use other systems for final project, but you're on your own if I can't happen to consult for them. Use an Arduino script language, you're on your own. I don't know that. You decide to use an ARM CPU running some micro C/OS. Well, I can help a little bit with micro C/OS. By the way, micro C/OS, very nice operating system, often free, very well documented, usually pronounced mucus. So, but yeah, good. Start thinking about final projects here, and we'll try and narrow it down. How many people would use a microcontroller if they could? Wow, really? What microcontroller? Some
Atmega.
Some Atmega, some
Mega and an XB, because XB is also Mega.
yeah, Atmega. What do you guys want to use? MSP 430 for the wireless.
Low power.
Low power. Okay.
16-bit architecture.
Yeah, that's nice too. Yeah. Okay.
Atmega.
The same with
Okay. I guess I'm okay with this. Like I say, it's sort of outside the teaching range for the course, but on the other hand, if half the class wants to do it, we'll just change the definition of the class. I mean, that's easy. Okay.